Hey guys, this is Mr. Isles and welcome to Geometer's Paradise. This is my 6th video that I am making so that you guys have a little hope for tomorrow. And I'm not going to be there. Man, I'm really sorry about this. What I've decided to do is introduce this new type of congruence because practicing this is going to help you with your side, and side angle, side congruence, which is what I had originally planned on doing today, before it just became totally clear that that wasn't going to happen. So what we're going to do here is just kind of go through angle, side angle congruence proofs. Basically, angle, side angle is just like side, and side angle, side. Oh, in case you're wondering why I'm not writing anything, it's because I left the tablet at school. So this is just a spectacular video in every way. So angle, side angle is a type of congruence where you're looking to prove that two angles and one side between those angles are congruent. For example, here, boy, I wish I had a. Oh, you know what? I can do this for this slide. Okay. So if I come in here and I'm like, hey, this angle and this angle are congruent to one another. And over here we have a similar kind of situation, like this, and then the side between them. This is an angle, side angle example. Okay, what's interesting is that angle, side angle is also achievable if you have something more like angle, angle, side. So for example, suppose I know this for this picture. This is enough information to prove angle, side, angle, even though the side we know that's congruent is this reflexive one over here. This is angle, angle, side rather than angle, side, angle. Well, the deal is that, you guys remember the third angle theorem? Oh, this is hard. Angle theorem. Oh boy, I'm so sorry. The third angle theorem, you remember that? Well, the third angle theorem tells us that this angle is congruent to this angle. And so that gives us angle, side, angle. So this is called AAS. And it is achievable as well. It's basically angle, side angle plus the third angle theorem. So instead of doing the third angle theorem, you can just see angle, angle, side and say, hey, that's a thing. Basically, you just need any two sets of angles and one set of congruent sides, and you're fine. This is in contrast to side angle, side, which doesn't work if you have angle, side, side. But angle, side, angle does work if you have angle, angle, side. So any two angles and a side, and you're good to go. No, I do not want to keep the annotations. Okay. So let's do an example. Here I have A is the midpoint of RE. So this is the segment, okay, that A is the midpoint of, which means RA is congruent to AE. So for my side, I write RA is congruent to AE. This is because of midpoints. Now, my first angle comes from the vertical angle, RAN and VAE. So angle RAN is congruent to angle VAE. Alright, this is the vertical angles theorem. Now my second angle comes from the parallel sides, here and here. I can actually pick either one. We're looking at the angles formed by a Z between the parallel lines and the transversals. So R and E are alternate interior angles. Also N and V are alternate interior angles, and you can choose either one. So I can say angle R is equal to angle E. Notice that I use the single letter names here. This is because there's no ambiguity here. This is the only R. This is the only E. So there's only one angle with that name. I can't use A, though, because there are 4 angles that have A as a vertex. But since R and E are the only angles that have those vertices, I can use angle R equal to angle E. This means that triangle RAN is congruent to triangle EAV by ASA. This proof also works by replacing this line. I can say angle N is congruent to angle V. Alternate interior angles theorem, and this would change the proof to an AAS proof. You can see it if you mark it up. It would be angle, side, rather than angle, side, angle. Okay. If you had chosen N and V and RAN and VAE, it also would have been an angle, side proof. Okay, that's a possibility. So let's see, there we go. Alright, let's expand that a little bit. There we go. So it's either one of those two, and you end up with either of those proofs. Okay. Elevator shaft. Okay. First of all, the side is the AK side. So AK is congruent to AK by the reflexive property. Alright. Now the angles, any two angles, right? So AK is perpendicular to HW. That means that this angle is congruent to this one. Call it 1 and 2 if you'd like, or angle HKA is equal to angle WKA. This is because of perpendicular lines. Perpendicular lines form congruent adjacent angles. We also have the bisector. AK is bisecting HAW up here, which means that angle HAK is equal to angle WAK by the bisector. So our triangles HAK and WAK are congruent by angle side angle. Okay, here we have the parallelogram, and this time it actually is a parallelogram. I'm saying that LY and XN are parallel, and that LX and YN are parallel. We have our reflexive side XY. So XY is equal to XY, reflexive. Now the angles that are congruent excuse me, are the ones formed by the Z. So LY and XN. So you see that? LY and XN. So that's this angle, LYX, and this angle, YXN. And LYX is equal to angle YXN, alternate interior angles theorem. It's almost always that. The other angle is formed by LX and YN. That's LX and YN. So LXY and NYX. LXY is equal to XYN. AIAT. So triangle LYX is equal to NXY by angle side angle. Finally, same deal. LE bisecting BLU, LE bisecting BEU. We have the reflexive side, LE is equal to OE. You have the bisectors on either end. So BLU, angle BLE is equal to angle ULE because of the bisector. And angle BEL is equal to angle UEL because of the bisector. And so this means that triangle BLE is equal to triangle ULE by angle side angle. And I know I've said equal a lot here. That's because I'm typing an equal sign. You should know that all of this is congruence, not equality. Okay? Hope this helps. Good luck with your notes. And I hope to see those of you not going to Disney World on Wednesday. If I don't, if you're going to Disney World, have the safest trip. Enjoy yourself, and I will see you on Monday.